Alright, safety requirements substantiation allowable the ice secretion and the primary habitat associated with the engine inlet icing potential for the damage caused with the travel of the ice ingested by the engine, secondary effects of the ice build with the possibility of inlet airflow to distortion blockage with which could affect the engine performance, analytical method to discover the previous detection drift of the ice acceleration rate with the DSL icing effectiveness of the ice fragments relieve the mass of the wave with the de-icing system should be considered with the engine inlet concurrently may be possible to estimate the icing accretion rates of the code described by the computer analysis icing de-icing section of the code to be based on the empirical studies simulated ice conditions information regarding shape and aspect ratio of the ice fragments from the inlet during the system operation best required for the same empirical study they give through the Ross estimate ice fragmentation side that might be ingested by the engine performance for the inlet ice the ice accretion rate with a function of the inlet shape of the meteorological condition aircraft the engine the operating condition of the maximum ice thickness for the created the engine inlet will be determined the particular de-icing system you have the properly designed so to keep the ice layer and therefore aerodynamically shaped over the ice and inlet pressure since minimum concern of the engine operation turboprop currently certified with the place ice condition with the engine inlet with or de-ice pneumatic boost although these turboprop inlets are small with their energy performance does not significantly compromise ice thickness of 1/4 inch minimum ice thickness, which however the de-icing system originally affected the pneumatic boot section and turbofan engines equal to the greater size inlet flow areas of the turboprop for this reason the accretion of 1/4 inch should be non-adversely affect the operation de-icing waters to be used on the engine inlets for the aircraft. Furthermore, expect that the new de-icing system will keep the ice minimum thickness of 1/4 inch. See the de-icing section ice accretion even less than concerning for inlets using new systems. Allowable ice ingestion affect the ice ingestion engine with the air taken into consideration during the standard during an analysis carried over the aircraft turbine engine with the manufacturer all aircraft turbine engines acceptable level of ice ingestion. Allowable ice ingestion is defined in two ways: maximum ice fragment and size 2, the maximum ice fragment quantity during de-icing cycle. For any turbine engine, one definition will result in a stricter limitation ice ingestion than the other. However, many of the engines made it advisable to define both values. The limit of the ice fragment size is usually set by which prevents any of the inspect damage for the engine component limited with the total quantity of the ice ingested during one de-icing cycle to define the limit above which ice will cover the intolerable shift of the engine operation such which might cover the engine surge or stall. Operating de-icing system can be presumable result of the acute damage of the engine during the infrequently shedding of the large ice fragments of the engine blade with the other component of both the rime and the glass ice type. Such an encounter expected with the result of the defined ballistic type of the soft body bird type that the threat to the engine structure under such conditions should not be possible to determine whether or not the damage has occurred or if or not whether the engine operation has been impaired. Many turbine engine manufacturers analytical method to predict engine ingestion capability. However, these methods of the proprietary information computer code are developed in engine manufacturer structural inspect analysis as empirically sustained by ice ingestion testing conduct fulfilled within Federal Acquisition Regulation Part 33 engine ice ingestion certification tests as well as the other ice impact tests. Whether or not particles separated due to the inlet and will the efficiency influence process of the matching of the engine particular inlet de-icing system. Although particle separators will not affect the ice ingestion tolerance of the turbine engine, it will allow the shedding of large fragments quantity of the ice of the inlet because of it depending on the performance of the separator most, if not all, shed ice bypass the engine. Probably most realistic concern of the inadvertently released loss quality of the accreted inlet ice regular release relative to the small fragment the quantity of the ice the turbine engine manufacturers have to determine the level of the ingestion but the engine component damage will not occur. The engine power output will not be affected simultaneously. The de-icing system must be evaluated to determine whether the shed ice is suitable size of the quantity such as the engine ingestion limits are set. But the possibility of the engine component erosion resulting in the repeated dose impacts may prove to be more cost maintenance concern rather than flight safety issues. Cumulative engine damage due to these less severe but repeated ice impacts result of the de-icing normal flight envelope should be readdressed in testing. Such testing should be defined shed ice for size at least in the thickness of the curve in such flight conditions. The assessment of the total number of these fragments will be countered by given flight. Engine manufacturers should evaluate the engine blading and the structure of the under such environment as well as the condition of operation engine following such damage. This effect requires the manufacturer to define separable damage limits of the engine to provide control that would maintain engine operation following the damage within these limits. Ice impact efforts on engine components. Ice release from the inlet result of the de-icing generally follow the flow of the streamline for the inlet impact with approximately at the same radius relative to the engine center line at which for the release of the here or the effect of the impact of various components of the engine. Both of the occur directly those of the result of the ice shatter on the fan. Acoustic liners for turbine engine aircraft that comply with the applicable noise regulation. Much of the inside of the engine inlets and bypassing ducts are covered with acoustic liners. Areas of acoustic liners might be located at area A between the inlet leading edge and fan face, area B in and just the rear of the fan rotor path, and area C along bypass rearward over the fan. Area A liners engine inlet diameter generally regard smaller than the fan face diameter of the ice release for the inlet leading edge for the easily does not impact the acoustic lines area forward of the fan. The acoustic search reported surface incident covering 24 million flying hours of the RB211 engines have now revealed no incident of damage for the acoustic liners at areas A that could be attributed to the inadvertent shedding of the ice. Area B liners ice could build up with the fan blades, creating out of balance condition. Except for the perceived in this situation, the dislodging ice increase the engine speed with a short period. With the dislodging ice may slide toward the tip of the fan blades, following the path that is determined by the blade shape of the fan speed. With the liners of the area should be designed to withstand the type of the repeated ice impact. Okay, figure 4.1 show the initial pass ice show the engine inlet meeting with acoustic liners and the engine lastly A and C the relative of the free from the impact and linear B subjected to the ice impact result of the ice dislodge on the fan. Have an inlet edge A and that's area A and then B in the fan rotor path and then acoustic liners A, B, and C. So they have the guide vanes between B and C. Fan rotor path at B, shedding fan ice at 1. B and C impact liners on fan bypass duct, accelerated accreted ice in A, and the compressor. Ice release from the engine inlet tends to the valve of the streamline to the engine with the track with the far near the outer edge of the blade with this impact with the fan shot over the ice and the impart with the high value with both the tangential axle velocity to with the due with the extra axle velocity as possible for the ice to the midst of the impact line over the area B with it hit the acoustic lining over the back over the impact lining. However, because of the ice packing when the fan close to the blade tip, it would hit liners for the only glancing with the blow of the ice impact region area B. These glancings blown would have less force of the imparted on the ice shred from the fan blades for which of the area line is just substantiated with the RB211 surface the record with the over 24 million flying hours over the only 3 engine inlets have the extreme of the ice impact damage to the liners on fan rotor path. The damage of the 2 inlets occur within the same aircraft, damaging with the same in the experimental flight. Other incident occurred with the aircraft where the center engine throughout with the ingested ice dislodged of the fuselage both of the aircraft undergoing specific ice testing trial at the time prior to the certification. Area C liners after passing through the fan blades, ice follows with a path parallel to the linear surface, therefore with the aerial zero velocity, zero impact moment in the direction perpendicular to the linear surface with no velocity normal to the surface of the ice passing through the outlet guide with the vanes. The OGVs down with the bypass duct can cover any of the damaged liners in those areas. With the search and the search reported service incident with all RB211s and have revealed no damage in area C could be attributed to either ice shed with the fan blades, ice shed from the inlet. Engine compressors on the modern day large turbo fan and the diameter of the fan inlet significantly greater than the diameter of the core of the compressor inlet. Since the ice of the release for the fan inlet would be expected to hit the fan blades approximate inlet radius, that it would not be likely to inject the compressor core with the damage should not occur with it, as the result ice being from fan inlet directly impacting on the compressor blade with the possibility of the damage of the compressor could occur directly by icing damaged fan blades causing engine surge as a result. A review with the RB211 and service engine incidents over the in 1972 revealed with a record total of 47 aircraft experienced with ice and snow ingestion that has an effect with 56 engines. The majority of these incidents result in little or no damage. However, the 14 engines sustained with the fan blade with leading edge damage and the secondary damage of intermediate high pressure compressors occur with the result of the engine surge with the all accident involved with the center of the engine with the tri-engine of the transport aircraft. The finding highlights of the need of the search for de-icing and snow removal of the fuselage, center edge inlets, S-duct, and the requirement has not always been recognized during the early operation of the aircraft. In no case, however, the core damage directly attributed to the ice relief of the engine inlet consequent de-icing. Inlet guide vane with no information pertaining to the engine manufacturer regarding tolerance of the ice damage. Inlet guide vanes which are found in front blades on some of the generally older engines. Many of the engines equipped with the outlet guide vanes or OGVs the function of the remove the rotational components for the air flowing, leaving the fan blade with the ice passing through the fan shatter with a high value of the tangential axle velocity imparted to the result of the lost ice passing through the outlet guide vanes with a low incident angle with which for the cause of the damage. Source 3 with the RB211 and serve with the incident in which the ice was thought to be involved performed no damage to the curve of the outlet guide vanes. Engine service record from the other engine manufacturers was not available. The confirmation of the conclusion fan blade damage could occur with sufficient large piece of the ice were released from the engine inlet with the impact of the test performed by the engine manufacturers using both ice and birds, but real and simulated, having demonstrated a high correlation between the permanent deformation fan blade leading edge and kinetic energy bird ice and normal surface of the leading edge of the kinetic energy threshold can be determined above the damage occurred with the blade, below with the no damage occurred with the figure 4-2 with comparing the fan mill. Similarly, if curves attain with the impact of the different of the positions along with the length of the fan blade, it found that if it becomes steeper, particularly with the blade tip of the ones of the kinetic energy threshold will exceed with a small increase of the kinetic energy will result in relative large increase of the permanent blade deformation. Ice is released from the engine inlet will most likely impact near the tips of the fan with the blades reaching the high sensitivity of the kinetic energy. Show the permanent local deflection blade tip of the non-dimensional radiuses, kinetic and normally blade leading effective edge, relationship between kinetic energy, normal fan blade leading energy, and fan blade methodology for determining the fan blade damage. If the ice is very likely to impact with the fan blades near the tip of the most vulnerable to the damage of the rather than attempting an assess with grade level of safety damage considerable to manifest to determine the maximum ice fragment size for the cause of no fan blade damage. One possible method calculating the presented here of the method is deliberately generalized for the application of different for the fan blade design flight condition of the engines operating with a different aircraft. The method determines whether the calculated velocity ice fragmentation hits with the fan blade with above or below the threshold velocity for the cause of the fan blade damage of the given ice fragment with given mass is based on the threshold levels of the kinetic energy normal to the blade at 1/2 of the meter's velocity critical with determining the impact state of the both wide chord and narrow chord shrouded bladed types of the methodology is followed. Step 1, selected ice fragment size calculated based on wind tunnel studies. Step 2, calculate velocity ice fragment in the fan blade row and engine flight condition inlet length. Step 3, calculate component relative velocity normal to the blade leading edge, blade geometry, assumed impact radius. Step 4, compare velocity normal to the blade and velocity critical back to the step 1 smaller with the fragment of the velocity, loading edge and critical with no damage. Step 1, initial step of the select the size of the ice of the fragment with a smite with a relief of the inlet, calculate the mass. The ice is assumed to have a split with the gravity 0.9. Step 2, once the ice fragment has relief of the inlet, it will be accelerated with the airstream. The throw of the fan blades accelerated force of the fragment instant will be the drag coefficient shedded the ice fragment dependent on the fragment shape of the drag coefficient of the differential fragment shape of the combined with the reference for 1 following example 1.0 cross section with the drag presented the ice with the airstream and the take with the average area with assuming with the ice fragment with the tumbles with the presenting as inside varying area with the airstream sensitive with the air parameter view with the flight conditions such as altitude, airstream, velocity with the usually occurring with the fan phase. None of the calculations assumed for the ice fragmentation tumbles in such a way one on the impact of the fan blade oriented with the whole mass of the ice fragment impacts on one fan blade with the worst case of the assumption on average sensitive the mass be likely the impact of the fragment will be divided between two blades shown in figure 4.3. The ice velocity of the ice mass, whereas density and volume velocity per increase per unit shows a velocity triangle with the ice impact fan blade leading blade splicing blade slicing path of the blade leading edge slice length ice fragment viewed by looking blades normal blade leading edge and sliding length. Cyclical computer program can be written with a small time increments of the enables the velocity with the derive of the inlet length with the typical relation between the ice velocity of the inlet length shown in figure 4.4. Step 3, assuming the ice will strike with a fan blow row at the same rate at the inlet which was released from the geometry of the fan and the blade velocity the ice velocity with the velocity of the triangle control is determined with the velocity of the ice relative to the movement of the blade. The component with the relative velocity of the ice and relative to the blade leading edge can be determined the velocity triangle. Step 4, the value of the velocity obtained with step 3 can be compared with the value of the maximum value of the velocity with no blade damage obtained with the figure 4.6 and figure 4.5 and 4.6. depending on whether the blade is wide chord or narrow chord type with the mass ice sheet. In this obtains step 1, non-dimensional the radius of the track with the radius of the same in the inlet in step 3, and the velocity greater than the critical velocity fragment side with step 2, but likely to cause the damage of the blade. The process of comparing the velocity of the blade and the velocity critical repeat the smaller ice fragment. The velocity of the blade smaller than the velocity critical velocity no fan blade would be expected the size of ice fragment selected. So it shows typical profile ice velocity increase the engine inlet length of the inlet length. Then it shows a variation of the critical ice mass, non-dimensional fan blade radius, width, wide chord fan blade, threshold velocity ice fragment at which damage occurs to the blade, variation of velocity cross ice mass, non-dimensional blade bias, narrow chord fan blade, threshold velocity ice fragment above the damage occurs to the blade. Example is used in this method given below. The basic conditions assumed and calculated in Figure 4. However, since the velocity of the fan blade is less than the velocity critical, no damage would be expected. The result of the impacts over the Figure 4 and 5, 5, and 4, 6 demonstrate that above the threshold level, the velocity critical damage increase very rapidly, even over the relatively small increase of the ice fragment mass, fan blade radius, particularly at the tip of the blade, for the reason that you set some acceptable level of fan blade damage becomes impractical. Ice fragment curvature, previously stated, conservative assumption that has been made regarding the orientation of ice fragment. If the whole fragment hit one over the blade, assume with the fragment the rectangular flat, which for the purpose of calculating impact force and part of the blade inadequate. However, the ice shape of the inlet, if the actually curve of the curvature result in the shape of the inlet with which is formed, because of the difference in the shape of the rectangular mass of the ice, assume the impact of the blade leading edge of the greater than velocity normally with the blade with the greater force of the curved ice that actually impacts the met blade. Figure 4.7 compares the flat and curved ice fragments with the worst case attitudes relative to the blade. Correlation of the velocity of the ice fragment mass and point impact on blade expected with the threshold velocity with the damage to the curve of the fan blade with the correlated to the mass of the bird and ice fragment. Shows actual ice fragment, assumed shape of the ice fragment. When be looking at the blade types and blade impacting the blade. Figure 4.5 and 4.6, in addition to the side of the impact, given the mass of the ice, move at the tip of the blade, damage with lower and lower velocities. In Figure 4.5, with the curve of the radius of the 0.9 is based with the data from the test of rotating blades with hit the bars and curvature of the radius of the 0.99, based with the data test of which of the cylinder of the impact stationary blades are statistically clamped together in bases used for the bird. Soft body data predicted damage result from the ice fragment impact justified with the base of the internal struggle generated with the ice cylinder substantial see the ice tensile strength, therefore both of the tree with the fluid jet impact with the similar with the density ice and bird result of a similar impact pressure on the fan blade. References 4 and 2 and 4 and 3. Generalization methodology. The other applications not suitable in this document cover all of the combination of the engine fan blade, the design flight condition of the ice fragment set with the method required for the adaptation of the use of the application for the engine study. For example, the criteria for the known damage base for the large turbo fan engine for the wide chord or shrouded narrow chord types, and for which the methodology have been substantiated with the reviewing service record for the other turbine engines, maybe the more or less prone fan blade damage per bird and ice ingestion, and therefore it would be necessary to derive the velocity for each particular fan blade design. General structure and analysis of the impact is dynamics. Expect with the injected ice fragments from the impinge of the forward part of the engine structure, the inlet guide being for the fan blade. Recent research of the foreign object of the damage of the fan blades have resulted in the development of a variety of the analytical techniques to try to predict impact process of the structural response over the blade. Purpose of the selection outlining the analytical approach. Approach of the first icing fragment, the trajectory is determined based on the information cited for the impact of the engine impact velocity was obtained. Next, model of the dynamic the ice impact process is developed based on the non-viscosity of the fluid mechanical theory type of the analysis of the independent corrosive strength of the impact icing, the use of the potential flow through theory with the representative of the complex mathematical analysis model with the ice impact. This in turn predicts the pressure distribution impact curve of the Figure 4.8 pictorial describe the process of the wearing of the bird other soft body object such as ice impact the territory of the velocity causing the shock velocity that propagate the opposite direction energy to the releasable tangent roll to the surface. This energy releases sets of the pressure of the distribution on the surface. Once the pressure distribution is known, this data can transfer the structural dynamic code NASTRAN to determine the blade response with a characteristic under ice impact approach 2 with another available approach make for the Dyna A3D computer code. This was a three-dimensional finite element code for the announcing large deformation responsible inelastic solids and structure. This code modeled 26 material with 11 equations and stable to analyze with a wide range of material behavior. The code containing algorithms simultaneously adding interference and ballistic impact. One to the code useful feature for the capability to model local failure. Selected model mesh for the modeling the breaking apart over the structure of the real eye with the using the element corners of the disconnect. When defined with the achieve the hydrodynamic modeling that is also available, which means the codes used to completely characterize the impact process. Safety issue with the de-icing system. Safety becomes occurrent with the de-icing system as a result of the damaged engine fan blades with the other components. Currently, the design of the de-icing system works for the engine manufacturer to determine the compatibility of the de-icing system with the engine manufacturer specified with the fragment and amount with the ice that ingested by the engine without damage. The de-icing system manufacturer to design his service system operate these conditions. Service experience with the indicator of the black damage pose a threat and safety only with exceedingly occur with the result of the impacts by multiple. Alright, shows target ice and shock, release shock, stagnation point, and determination. 1.5 pound bird demonstrated the medium size of the bird ingestion type of the currently conducted within the Federal Acquisition Regulation 3372 that opening 1 inch of the manufacturer replaced with the ice damage blade with will maintenance for the control of the aircraft with you with the rather shear with safety condition de-icing system releasing ice fragments which called small with dense blade with edges could after several icing encounters over the only cause cumulative damage denting to the finally exceed the acceptable limit of the respect of the engine manufacturer maintenance specification. This becomes an economical concern for this aircraft when who must decide whether to replace or repair the blades. According to one of the engine manufacturers, cumulative denting only becomes a safety issue if it exceeds medium-sized bird strike damage, which may be a factor of 100 or more greater than the ice caused the denting described above. Safety precautions apply with the de-icing systems. This section describes safety precautions, checking the balance of the distributed design with the de-icing system. With the cycling times, contemporary de-icing systems are operated manually or generally aviation aircraft with automatic systems is one activated with continuous cycle deactivated with a pilot. Manual system cycle 1 per pilot activation. Most commonly automatically operated turbine engine inlet de-icing systems are electrothermal system and the pneumatic boots. The most critical concern with the setting of the timing with a cyclic does the ice over the ice with the accretive of the de-icing cycle that had limited with the levels of that can be tolerated with the engine such as ice or shev. The cycle timer involved with accretion rates must be determined at all flight regimes. Worst case accretion rates may be used to set with the maximal level site interval with the mechanical de-icing offers more flexible thermal systems controlling de-icing timing cycle due to the operational characteristic anti-icing system. Large ice ingestion has been addressed with the worst case situation in which all potential accreted ice assumed and ingested requirements are based on Federal Acquisition Regulation 3377, the delayed actuation of anti-icing system accreted to ice. The approach will not be applicable to the de-icing system activated with the de-icing system. Only remove the portion of the inlet where the anti-icing system activated removes the ice air in entire inlet at the same time. Therefore, the amount of ice in the engine ingests of the worst case situation in the de-icing system less severe than when it was anti-icing system. The zone by zone de-icing air inlet advantage of the de-icing system will meet with the ice ingestion tolerance engine. To do with this low ice ingestion tolerance engine must be known fragment size with the amount of ice shed particle to the de-icer must be evaluated whether the falls within the engine ingestion limited to the cycle internal for each zone will be set to avoid accretions beyond which they were tolerated. Engine with the ice shed with the ingested. This is based on the worst case accretion rate, particular inlet geometry, proprietary reason ice ingestion tolerance of the engine were not available to inclusion in the study. Alright, water runback, electrothermic de-icing with need of a design with a minimum water runback, common technique with control of the water runback well, except for the power consumption. Alternately, the de-icing zones with the air to be protected forward. Some undergo the de-icing cycle with the first, cause some of the water to run back unheated at end zone, where the water in the free and the end zone undergo the de-icing cycle with the removal of the now frozen runback water. Particular separation. Many turboprop helicopter engines are equipped with a particular bypass duct with a minimum engine ingestion ice or foreign object allows longer de-icing cycles. Intervals would be allowed. The no particle separation. UVD engines are generally small but inherently more sensitive to the ice ingestion. Large high bass turbine fan Engines. Low turbine fan engines do not know or probably not incorporate particles separated from those now used in small engine helicopter turboprop. This means the ice will pass directly into the engine, impact the fan guide vanes, and possibly the acoustic panel. For these engines, the de-icing cycle must be set with a minimized size and quantity of ice shape of the engine. Ice detector. The ice detector is part of the automatic closed looping sensing with the auto actuator system. De-icing will select with the de-icing cycle. The timing ice detectors will actuate the de-icing only when ice is actually present. Whenever the pilot with the actuator with the de-icer fixed with a predetermined cycle of time, either with the icing or the suspected after ice with created with the visible level of the aircraft exterior with the zone by zone de-icing using a number of ice sensors distributed around the circumference of the inlet could negate the eventual automatically controlled ice release system, and if all the detectors instantaneously actuate de-icing in their individual zones, excessive potential damage quantity of ice can be released into the engine. Summary. Only a small percentage of engine manufacturers currently have a de-icing system, mainly with the electrothermal heater for the pneumatic boots. De-icing system will play an increased role in the future aircraft turbine engine inlet icing protection. Engine manufacturers facilitate you with the engine and efficient the de-icing system proper attention to detail the design development qualification of new propulsion system by defining acceptable approach criteria that do not adversely affect the flight safety, fuel safety, and reliability of the option de-icing system instead of the anti-icing. Analytical method cannot be found with determined side of the amount of the ice shape during the de-icing. The inlet lip empirical method you would identify with the method to suggest the high-speed camera to be used to record ice shedding process of the ice fragments released from the inlet with a characterized exit prior to the input. Acting any object, the braking of the method is described in the title of the engine manufacturer ice experience. The analytical method predicted ice fragments impact locations identified with determining which part of the engine inlet is sustained with the damaged ice dislodged by the inlet during the de-icing. The first step of the analyst determine the trajectory of the shedded ice for this existing particle trajectory. Computer codes applied with the predicting path of the shed of the ice fragment. The trajectory analysis identifiers for the engine of the component impacted by the ice, such as acoustic liners, fan blades, engine core, guide vanes, parallel to in lieu of the trajectory impact analysis. The engine service records may supply information regarding the engine components of the suspect of the ice damage. Here to the success of the records resulted in several discoveries versus over 24 million flying hours, not than 1 inch of the damage of the acoustic liners have been attributed to ice shed from an inlet, nor has there been any direct ice damage for the engine compressor, for the outlet guide light vanes, although some of the secondary damage of the engine one core resulted from the fan blade caused by the ice. As severe fan blade damage occurred with the tip of the fan blade. Severe fan blade damage critical because the cause of the engine surging. Two analytical methods have found with the predicted the severity of the fan damage of the caused by ice impact with the describe the section entitled Ice Impact Effect with the engine component of the general structural analysis and impact dynamics. Ice accretion rates that may be determined the various ice conditions due to the computer code to discuss computer analysis icing de-icing section. The accretion with the control of the matching timing of the de-icing cycle with the rate of the ice accretions. Time of the de-icing system would present with an interval between the de-icing cycle and is short with enough to keep the accretion at a tolerable level, the level at which airflow and not impeding the ice fragments were released during the icing due to the damage of the engine. Instead of the automatic de-icing system could use the ice detector same with the rate ice accretion with mass of the timing of the cycle of the ice conditions. No information available to open the literature reading along with the amounts of the engine inlet ice accretion and any of the associated performance penalties. The detector for the manufacturer report of the ice detector development is now advancing icing advisory stage with measuring ice accretion rate and ice thickness. However, the integrated sensor de-icing systems will only occur if there's reliability ensured. The technology surveys conducted as part of the research effort to predict the mid-1990s time frame of the de-icing system with a large scale of the application new generation engine smaller compared with a large diameter frame with a more advanced turboprop engine with less energy available to the operating anti-ice system. This does mean with the de-icing is restricted only in future applications. Several type of the engine currently with a service with a suitable from the shift of the anti-ice with the de-icing turbo shaft of the prop plane with the ducted profan turbojet engines are likely to come with the motivation with the shift of the desire to conserve energy with the proper process certification de-icing system turbine engine inlets and expected to be very different than now you with the certification any of the other inlet icing protection system certification procedure for the include with the design analysis phase of the ice wind tunneling testing you with a model with existing tunnels too small with the actual inlet see with the icing flying test the ice wind tunnel test may be set to simulate with the actual projected insulation geometry operating methods have not been recorded with a large contemporary turbofan anti-icing system since the no engine and NASA with the various existing insulation with little or no change required for the anti-icing system design and operation due to the maturity of the current anti-icing system with the large turbofans analysis. Either dry or ice flight testing has been provided adequate certification. Some of the transport aircraft using de-icing system proposed use of large turbofan prop fan engines reaching a level of competence valve with the anti-icing system. Icing ground tests probably would need to demonstrate the de-icing performance. A diagram process for the inlet de-icing should undergo the above certification shown in Figure 5.1. Here the emphasis for the place on the major concern for the de-icing system: ice acceleration and shedding of the ice impact of the damage analysis due to the lack of data of the new system and the NIMI both resulted from the law system designer demonstrated by the FAA with the system function properly. Critical design conditions of defined critical design conditions can be met. Various loops in the path of the certification level of the system of the designer to modify the system orientation necessary for the configuration that will ensure the safe engine aircraft operation in icing conditions. In conclusion, inlet de-icing system certification, aircraft operation condition, meteorological conditions, into water catch accretion analysis, icing test, de-icing system into design operation goes into shedded ice trajectory impact analysis, impact testing, then design icing system operation. From those two into the impact design structural analysis, impact design testing, and then from there it goes back to the de-icing system design operation. From the impact design structural analysis, impact design test, long-term impact, conventional durability, and reliability test, certification test, the FAA certification, and then conclusions, and then appendix references. We'll cut the tape there, and I'll take a brief look at the appendixes.